Last time we talked about summary of curve sketching. We talked about the factors that we need to consider when we graph the curve of a function. The following factors are including the domain of a function, the intercepts, okay, the intersection with x and y axis, and symmetric, if it's even, then we know it's symmetric with respect to the y axis. If it is odd function, then we know it's symmetric with respect to the origin O. Your symmetry very often, then we can reduce half the work. Okay, asymptotes. We need usually we do horizontal asymptotes, vertical asymptotes, but sometimes we have slant asymptotes. And per E, increasing or decreasing intervals, we use increasing decreasing test. If the derivative is positive, then we know the function is actually increasing. If the derivative is negative, then we know it's actually decreasing on that interval. Concavity. G is concavity. So the concavity test says if the second derivative is positive on an interval I, then the graph is concave up. If the second derivative is negative, then the graph concaves down. Local max, local min. So this is the use first derivative test. And then once we have all the information, we try to combine all the pieces of information together and then sketch the curve. Now we will do some examples of this curve sketching. So let's see this example. Let's choose this function y to be y over x squared minus 4. So first, it's domain. The domain. Now the domain is all the functions, all the values, all the values of x such that the denominator is non-zero. Okay, so we know x is not equal to 4, so x is not equal to plus minus 2. So its domain is all real numbers except plus minus 2. And then the symmetry, you see, it's symmetry. Y is odd, okay? Y is odd function. This is the odd function. So let this be fx, is this thing. So the function fx is odd. Fx is even, sorry, is even. Because here, the only factor that has x is x squared. So then if we plug in negative x, then we get, negative x squared minus 4, 1 over z. This is the same thing as we plug in x, okay? So in this case, fx is even, okay? Fx is even. So it's symmetric with respect to the y-axis, okay? So its graph is symmetric with respect to y-axis. And then we find increasing, decreasing, okay? Concave up, concave down, concavity. So we take its derivative and the second derivative. So we take a derivative. So y derivative, we take derivative of the thing. Now use power rule and chain rule, okay? Or you use quotient rule. Squared, then we have negative x squared minus 4 derivative. Then what we get, rearrange this. So we get negative 2x x squared minus 4 squared. Okay, now we need to find when the derivative is positive, when the derivative is negative. Okay, now you see the denominator is always positive. So if y prime is positive is equivalent to if only if the denominator is positive, if only if the numerator is positive. Okay, if only if the numerator is positive, i.e. X is less than 0. Now of course x not equal to negative 2. X is not equal to. Now y derivative is negative if only if the numerator is negative. This is equivalent to x is a positive. Okay, x cannot be positive 2. Okay, So we are done with first derivative. Now let's find its concavity by looking at its second derivative. So the second derivative can be done by the following. Okay, second derivative. Now we take derivative of, again. Now use quotient rule. Now we need to use quotient rule. Okay, quotient rule. Numerator, denominator squared, and then negative 2x derivative multiply denominator fixed minus negative 2x keep fixed multiply denominator take a derivative. Okay, so this will be negative 2x squared minus 4. Okay, minus 2x. So this is positive x. So it's positive 2x times 2x x derivative x squared derivative get 2x. Now 4x 4 its derivative is 0. Okay, 0. Okay, sorry. Did I miss something? Yes, I think I missed something. So the denominator should be squared. Sorry, this will be squared. So this will be squared. Sorry, this is wrong. This square derivative. Okay, so this is squared. This is power 4. This is inner derivative. So we also need to multiply outer derivative. So this will be So this will be 2x squared minus 4 power rule on the chain rule. 2x minus 0. Okay, this is right now. Okay, then you see we have a common factor x squared minus 4. X squared minus 4. If we cancel a factor of x squared minus 4, then what we get is simplify it. Denominator is degree 3 power 3. Now this is negative 2 times x squared minus 4. We already canceled a factor x squared minus 4. Then what's remaining is 2 times 2x, 4x. 4x times 2x. Okay, so this is the 8x squared. Okay, 8x squared. Okay, 8x squared. Then what is remaining is we simplify this again. So this will be negative 2x squared plus 8 squared. 8x squared over x squared minus 4x cubed. And then this will be 8x squared minus 2x squared. So 6x squared plus 8 over x squared minus 4 cubed. Now, you see, we need to determine when this thing is positive or negative. First of all, the numerator, 6x squared plus 8. X squared is non-negative. So if we plus 8, then it will be positive number. So the numerator is always positive for what value of x. Now the denominator, so second derivative is positive if only if the denominator is positive. Okay, if only if, so this is cube, if only if this factor x minus 4 is positive. Okay, if only if, solve this quadratic inequality, x greater than 2 or x less than 2, less than negative 2. Okay, so the remaining thing, if y derivative is less than 0, if only if, the other way around, if only if x squared minus 4 is less than 0, if only if x is bounded from 2 to negative 2. Okay, now we know when it's second derivative is positive or negative. So we can combine all the pieces of information all together. Okay. Now you see the boundary values of x is you see it's 0. We see it's 0 and plus minus 2. Okay. So look at the boundary value. Look at the boundary value of x. Okay. In first derivative and second derivative, and then we can come up with the interval notation. Okay. So we have 0, negative 2, positive 2. Okay. So this part is this number line into interval notation. So we put the interval notation here. -2 to 0. Now it's symmetric, so it only needed you only needed to plot, half of the work. Now y derivative, first derivative, second derivative, and the function y, and put everything in this table. Put everything in this table. Okay, from -infinity to -2. When x is less than 2, first we plot maybe second derivative. Now we know second derivative is less than 0. Okay, look at it here. Second derivative. Second derivative is less than 0 when x is from -2 to 2, -2 to 2. So this is negative. This is negative. Okay, so we are done with the other. The remaining, the complement is actually positive. Okay, so we are done with the second derivative. Now look. Now we see. Let's see what the first derivative. First derivative is determined by the factor x. Okay, determined by the factor -2x. So if x is positive, then the first derivative is negative. So it's opposite of the sign of x. Okay, so from -infinity to -2. So this is x is negative, then y prime is positive. Y prime is opposite of x. Its sign is opposite of x. So here from x from 0 to 2, x is positive, then y prime is negative. X from 2 to infinity, x is positive, y prime is negative. Okay, so we are done with first derivative now. Now, by increasing decreasing test, y from the interval -infinity to -2, y prime is positive. So this tells us it's increasing. And concavity, how about the concavity? Second derivative is positive. So by the concavity test, we know it's concave up. Okay, concave up. Now this is a increasing concave down. This is a decreasing concave down. This is a decreasing concave up. Okay, and then we plot its graph. Okay, so increasing concave up, what does it look like? Increasing concave up. So if you, according to the 4 combinations, so we have increasing concave up. Okay, increasing concave up, increasing concave down, increasing concave down. Okay, increasing concave down. Now in decreasing concave down, looks like this. Okay, and then decreasing concave up. Okay. Another thing is, do we have vertical or horizontal asymptotes? Vertical or horizontal asymptotes? Vertical asymptotes. How do we find vertical asymptotes? Now, vertical asymptotes is determined by this limit x approaches infinity, fx. Plus minus infinity. Okay, plus minus infinity. Here in this function is a even, so we only need to work out one direction. Okay, we only need to look at the infinity at positive infinity, the limit at positive infinity, because it's a even. Okay, now this is the limit x approaches infinity, 1 over x squared minus 4. Now this is very obvious. As x becomes absolutely large, x squared minus 4 can be absolutely large. So 1 divided by an absolutely large number. So this limit is 0. Okay. So we have horizontal asymptotes. Sorry. Oh, this should be what I'm talking is about horizontal asymptotes. Horizontal. X approaches infinity, so we get horizontal asymptotes. So this implies we have horizontal asymptotes, the x-axis. Horizontal, we have horizontal asymptote, x-axis, simply just x-axis. Okay. Now vertical, how about vertical? Now you see when x vertical asymptotes. Now we need to find when the v value approaches infinity. When the v value approaches infinity. Now you see x as denominator approaches 0, the numerator is fixed 1. So then the value can be arbitrarily large. So we need it, when x approaches 0, i.e. x squared approaches 4, i.e. x approaches plus minus 2. Then the y value approaches infinity, plus minus infinity. Okay, plus minus infinity. Then we get vertical asymptotes. This we get vertical asymptotes. Vertical asymptotes. Which will be x equals plus minus 2. Okay, so combine all this information together, we can plot. Okay, we can plot. Now, this is symmetric. Now let's do so this is 2. This is 2, this is negative. Okay, so we have a vertical asymptotes at 2 and a negative 2. Okay, from negative infinity to negative 2, let's check. From negative infinity to negative 2, then it's concave up. Okay, from negative infinity to negative, it's concave up, increasing. Now, as x approaches concave up, increasing, and as x approaches the negative infinity, it approaches the value approaches 0. So it has horizontal axis, x-axis, and then it's concave up, increasing, Okay, so we are done with the piece, negative infinity to negative 2. And then by symmetry, we can get 2 to a positive infinity by this part. Okay, so get this. The other piece is by symmetry. Now from negative 2 to 2, now it's you check from negative 2 to 0, it's increasing concave down. Now when x is 0, when the y-intercept. When x is 0, then y is now 0 squared minus 4, 1 over z, which is negative 1 over a quarter. So negative a quarter. Suppose it's here, somewhere here. Okay, negative a quarter, this point. Now it's it's increasing concave down, Now it has the vertical asymptotes as negative 2. Okay, so it's increasing concave down. Okay, so we're done with this piece. And the other piece, by symmetry, we plot the other piece by symmetry. Now, okay, it's only a rough graph. So it has the other piece by symmetry. So it's a decreasing concave down, So you see this symmetric with respect to the y-axis because it's even. So we are done with this graph. Okay, then we are done with this graph. Okay. Okay, the key to work on this kind of problem when you are given an explicit formula of a function is first look at the domain, solve its domain. Then find its symmetry, find its even or odd. And then find its first derivative and second derivative, and determine when the first derivative is positive and negative, when the second derivative is positive and negative. Okay, and then find its concavity and find its increasing, decreasing intervals. Okay, and then find its horizontal asymptotes, vertical asymptotes, and then combine all this information together. Okay, and also xy intercept if they have xy intercept, and then combine all this information together and then plot. Okay. Any questions with this problem? Okay, let's see another problem which is a little maybe easier. Okay, let's see this problem. Y dx power 4 minus 8x squared plus 8. Okay, let's plot this graph. Let's plot this graph. Let's plot this graph. Okay, first of all, so check its domain. So this example, new example. Check its domain. The domain is here it's polynomial, so it's defined everywhere. So its domain is all real numbers. Domain, all real numbers, all real numbers. Okay, all right. And then it's symmetry. Symmetry. Let's look at for symmetry. Symmetry. Now, first of all, you see we only have even powers of x, so it's an even function. Okay, even function, even function, even function. So we know it's a symmetric with respect to y-axis. Okay, symmetric. Symmetric with respect to y-axis. Y-axis. Okay, so we get a symmetry. Now, then we determine it's a interval of increase or decrease. Okay, and find this concavity. So we first take a derivative, y prime. Now take a derivative. Now this will be 4x, this distribute. So x cubed, 4 times power, okay, 80 times 2x plus 0. Constantly has 0 derivative. So we get a 4x cubed minus 16x. And then we factor, common factor you see is 4x, x squared minus 4, okay. And then this by difference of two perfect squares, then this we can factor it as x minus 2x plus 2. And then we determine when its interval of increasing, when the derivative is positive or negative. Okay, so here we have three factors. So if we let y prime be 0, then we have 4x, x minus 2, x plus 2. This is 0. So then one of the factor is 0. So this would be x0 or x minus 2 is 0. Or x plus 2 is 0. So we get x equals 0, 2, or negative 2. So it has three roots. So we have 0, 2, minus 2. Okay, and then we look at its interval. Okay, and see when y prime is positive or negative. Okay, now how do we work out? Now you can, one way is you can plug in numbers from each interval and determine whether it's positive or negative by special value, okay? And another method is you can use this method. So first of all, if x is large, then it's positive, okay? Every factor is positive if x is large, okay? And then once you pass through a root, then if it's even power, it doesn't change its sign. If you pass through a root, then you have all the power, then it changes sign. So that every time you have all the factor, all the multiplicity of root, then you change its sign, okay? So now you see this, well, every time here we have those three factors, x, x minus 2, x plus 2, they are all power 1, okay? All the power. So every time it change flip sign when we pass through a root. So it change sign. This part is positive, this part is negative, this part is positive, this part is negative. Okay. Then this is a quicker way to work out the sign of derivative. Okay. So we're done with, then we know the interval of increasing and decreasing. Okay, for y prime for the function y. And then we find second derivative. Okay, second derivative. And we take a derivative again. Derivative is 4x cubed minus 16x. We take a derivative again, then we get 4 times 3x squared minus 16. So this will be factor out of 4, 3x squared minus 4. Okay, so the two roots is 4 times root 3x plus 2 root 3x minus 2. Factor it. So it has two roots. y prime is 0 tells us equivalent to x is plus minus 2 over root 3. 2 over root 3. Okay, 2 over root 3. Okay, you see the graph, if you plot the graph of y prime, so it actually, it has two roots. It has two roots, negative square root 2 over 3, positive 2 over root 3. Now it's quadratic, it's concave up quadratic, so it's very easy to find this graph. Just a rough graph to determine when second derivative is positive or negative. Okay, so it's a quadratic concave up with two roots, two intersections with x-axis. Okay, so it's y prime equal to 4 times 3x squared minus 4. So this part is positive, this part is positive, this part is from negative 2 over root 3 to positive 2 over root 3. This part, is negative. Okay. Okay, so we know the intervals of increasing and decreasing, the interval of concave up and concave down. And then you see we find the roots of y prime and y second derivative in terms of y coordinate, in terms of y number line. So we have 0 plus minus 2. So this is for first derivative when first derivative vanishes. And then for second derivative, we have 2 over root 3 plus minus. Okay. So if you put all the numbers on the number lines, it's symmetric. So now remember, 2 is greater than 2 over root 3. 2 over root 3 is around root 3. Remember, root 3 is around 1.732. Okay. So this is 2 over root 3. 2 over root 3. Slightly bigger than 1. Okay. Now this is by symmetry. This is negative 2 over root 3. This is negative 2. Okay. And then we can, you see, we have a bunch of intervals. This numbers partakes is number line in terms of intervals. And then we put interval notation. And then this we get negative infinity to negative 2. Negative 2 to negative 2 over root 3. And then negative 2 over root 3 to 0. Now of course, you can plot just half of the work. The other half, we just follow by symmetry. Okay. Now let's just plot this by half the work. The other half follows by symmetry. Okay. So let's just y prime, y second derivative, and y. Okay. So we just be a little lazy here. Okay, now y double prime. This is, you check from negative infinity, so double prime. Okay, y double prime. So this is the y double prime. What we just did, y double prime is positive when x is negative, from negative infinity to negative 2. Okay, this is the positive, and this is the positive, and this is a negative. Okay, so we determined y double prime, and y derivative. You see, y derivative from negative infinity to negative 2 is negative. From negative 2 to 0 is positive. So the other negative 2 to 0 is positive. So they are positive here. So we can, by increasing decreasing test, so y prime here, the first interval negative infinity to negative 2. Y derivative is negative, so it's decreasing. And the concavity is concave up, okay, concave up. So decreasing concave up, what does it look like? Decreasing concave up. Decreasing concave up. Okay, this is decreasing concave up. And then the other piece, the second interval, is increasing concave up. Okay, increasing concave up. And then the third interval is increasing concave down. Increasing concave down. So increasing concave down looks like this. And then we plot its graph, and then look. So here it's a polynomial. Polynomial has no asymptotes. Okay. And look at its y-intercept. Y-intercept. Okay. The function. Look at the function. Here is x. So the function is y is 4 x power 4 minus 8 x squared plus 8 plus 8. So when x is 0, y is 8. Okay, when x is 0, y is 8. Y is 8. So let's plot this graph. Plot this graph. Plot this graph. Okay, remember the special value. The special value. We need to take consideration of the special value. So i.e., what happened at the coordinate? Okay, what happened at this coordinate? So for instance, what is the value if x is 2? X is negative 2, x is negative 2 over root 3. Now we look for the special value. Special value. So in this case, 1 is negative 2 to the power 4 minus 8 times negative 2 squared plus 8. You can use a calculator or you compute by hand. It's not that bad to compute by hand. It's 16 minus 32 plus 8. So it's negative 16 plus 8. So it's negative 8. It's negative 8. So when x is root 2 over root 3 or plus minus, x squared is 4 over 3. 4 over 3. Then y is x power 4. So it's a squared. So x squared minus 8x squared plus 8. So this is the 4 over 3 squared minus 8 times 4 over 3 plus 8. Okay, so this is 16 over 9 minus 8 over 3. Minus 8 over 3. So this will be 16 over 9 minus 24 over 9. So it's a negative 8 over 9. Negative 8 over 9. So it's around negative 1. So let's plot. Let's plot. When x is 0, y is actually 1. Y is 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is the y coordinate, y intercept. Then when x is root 2, 2 over root 3 negative, so it's around slightly bigger than 1, slightly big magnitude is. So this is negative 1. Okay, this is 8. This is 8. Okay, so when x is that number, then the value is negative. So this is negative 1 here. So it's around. So the value is around negative 1. So suppose it's somewhere here near negative 1. Okay, so this is this. And then when x is 2. When x is 2, it's negative 2, it's negative 8. It's negative 8. Negative 8. Okay, negative 8. So it's negative 2 here. Since it should be here. Okay. Okay, now let's plot. Now let's plot. From negative infinity to negative 2, it's decreasing concave up. Decreasing concave up. Okay. Decreasing concave up. From negative 2 to root 3, it's increasing concave up. Okay, increasing concave up. Increasing concave up. Then from root 3, 2 over root 3 negative, it's increasing concave down. Now here we change concavity. Now it's hard, a little hard to plot. Because the scale is too small. Okay, so here we change the concavity at negative negative 2 over 3. Okay, and then the other follows by symmetry. It's a decreasing concave down, decreasing concave up. So decreasing can go up. Okay, decreasing can go up. Okay, decreasing can go up. And then we can follow by symmetry, plot the other half, plot the other half. This is the y. So it just follows by symmetry. Followed by symmetry. And then change concavity. Change concavity. And then the other piece. Okay. Then we're done for this graph. Okay. Then we're done for this graph. Okay. This is this example. Okay. More example. Here we no longer have explicit formula, but we giving information of derivatives, derivative and second derivative. Okay. This example. So we are given a function such that f derivative equals f second derivative, f derivative at 2 and equal to f derivative at 4 is 0. Okay, and then we have f derivative x is positive if x less than 0 or x from 2 to 4. F derivative is less than 0 for the complement. If x is from 0 to 2 or x greater than 4, Now second derivative, f second derivative x is positive if x from 1 and then to 3. And then f second derivative second derivative x is less than 0 if x less than 1 or x greater than 3. Okay, now plot a graph of f that satisfies all the given conditions. Okay, if we have this kind of problem, the first thing to do is we try to gather all the information, put all the information together, and then use the table notation, put it in a table. Now, we first break into intervals. Okay, break the number line into intervals. First question is, what interval do we use? Okay, what interval do we use? Now, first we put all the numbers, all the boundary values of x into the number line. Okay, into the number line. So here the boundary values of x is, you see, we have 0, we have 2, we have 4, we have 1, we have 3. Put all these numbers of the boundary values of x into number line, on the number line. Okay, so we have 0, 1, 2, 3, 4. And then all these boundary values parties is number line in terms of intervals. Then we can write down the interval notation. You see, from negative infinity to 0, from 0 to 1, from 1 to 2, from 2 to 3, from 3 to 4, and then from 4 to infinity. Okay, so this is all the intervals. And then we have f derivative, f second derivative, and fx. Now we put all the information on this table, onto this table. Okay. Okay. Okay, let's look at the first derivative. First derivative is positive from the given information. First derivative, just look at the the first line on the screen. So it tells us that f derivative is positive if x less than 0. So this is positive, less than 0 if x is less than 0, or x from 2 to 4. Look for the interval from 2 to 4, 2 to 3, 3 to 4, this is 2 to 4. So this is positive. Then the complement, the others, f derivative is negative. So then we put the others into negative. Okay. Now we look at the second derivative, f second derivative. Look at the first line of this screen, on the screen. So f derivative is positive from x from 1 and 3, 1 and 3. So it's 1 to 2 positive, 2 to 3 is positive. Oh, so sorry, it's second derivative source. It's not f. So it's positive from 1 to 2, 2 to 3. And then the remaining less than 1 or greater than 3 is negative. Okay, then we combine all the information together and see what happens to fx. Fx, then we have increasing, decreasing test and concavity test. So this will be increasing, okay, concave down. This will be decreasing, concave down. This will be decreasing, concave up, okay. This will be increasing, concave up. This increasing, concave down. This decreasing, concave down, okay. Now if we plot a rough graph for each interval, so it's increasing, concave down, increasing, concave down, looks like this. Now decreasing, concave down, look like this. Decreasing, concave up, increasing, concave up, increasing, concave up, and then increasing, concave down, increasing, concave down, okay, increasing, concave down, increasing, concave down. Now decreasing, concave down, decreasing, concave down, okay. Then we combine all the pieces of information together. Remember, we have another condition which says the derivative vanishes at 0 to 4, 0 to 4, derivative vanishes. Derivative vanishes tells us we have a horizontal tangent line. We take a little care of that, okay? And then we plot a graph. So this is x-axis, this is y. So we are, so the number line is, so we have 0, 1, 2, 3, 4 is, all the thing is positive numbers. So we try to give more space to positive numbers. So this 1, 2, 3, 4. Okay, this is y. Okay, then from we look at each piece. Okay, negative infinity to 0 is increasing, concave down, increasing, concave down. Now from negative infinity to 0 is increasing, concave down. So we just plot the thing, increasing, concave down, and then decreasing, concave down from 0 to 1, decreasing, concave down, decreasing, concave down. Okay, and then decreasing from 0 to 1, and then from 1 to 2 is decreasing, concave up, decreasing, concave up. Remember, so horizontal tangent line at 0, so this is f derivative at 0 is 0. Okay, horizontal tangent line at 0, and then from 1 to 2, it's a decreasing, concave up, decreasing, concave up, decreasing, concave up. Okay, from 2 to 3 is increasing, concave up. Okay, increasing, concave up. 2 to 3, increasing, concave up. So this 2 to 3, concave up, increasing, concave up. Okay, increasing, concave up. From 3 to 4, it's increasing, concave down. Okay, increasing, concave down. So we actually change the concavity, increasing, concave down. Now, again, at 4, it's a horizontal tangent line. The rate of vanishes from 4 to infinity. So it's decreasing, concave down, decreasing, concave down, decreasing, concave down. Okay, 4. Now you see at 0 to 4, we have horizontal tangent line. Okay, horizontal tangent line. Okay, so the derivative at 0 to 4 vanishes. Then we are actually done for this problem. Okay, for this problem we're done. Okay. Any questions? Any questions? Okay, all right. Now let's do the next section. Next section. Optimization problems. Optimization problems. Okay. Now this section is really important actually. You know, in reality, we need to make the best possible choice from all the information that we have. For instance, if you do business, you want to maximize your profit, you know, and also minimize the risk. And also, for instance, in machine learning stuff, sometimes you need to do optimization to find the best possible solution. All right, let's see some examples how we actually use the max optimization. Use the max optimization thing. Okay, optimization. Let's see examples. Example. Okay. Suppose a farmer. Let's see this example. A farmer. Suppose a farmer has certain length of fencing. So suppose a farmer has 2,400 feet of fencing, and he wants to include a rectangle that has the maximized area. Okay, now he wants to include a rectangular field along a river. Okay, along a river. Okay. So now the river actually offers a natural boundary. So he needs not use fence along the river. Okay. He doesn't needs no fence along the river. Now the question is, what are the dimensions of the field that has the largest area? Okay. The question is, what are the dimensions of the field that has the largest area? Okay. Suppose we have a river. Okay, suppose we have a river. So this is river. Now, the farmer includes a rectangular fencing. Okay, first question is, now if the farmer wants to include all the, the maximum area, so he should use everything. Okay, use all of his fencing. Okay, so that should no leftover. So it's rectangular. Now, so we should determine, we should find what actually determines the area. Now the area of the rectangular is very easy to find out. It's length times width. Okay, length times width. So first of all, let's suppose its width is x, and length is y. Okay, length is y. So first, once you have this kind of practical problem, try to plot a graph and then put variables in it. And then find your goal function. The goal function is the area function. The area is goal function. Your goal function is to maximize is actually area function is length times y. Okay, length times y, x times y. Okay. Now here we have two variables, x and y. In general, in this course, we don't know how to optimize two variable functions. Then we try to transform these two variable functions into one variable functions. Okay, so that we need to find a relation between x and y. Okay, we need to find the relations between x and y. Find the relation between x and y. Then here we check what other conditions that we haven't used yet. So here the farmer has 2,400 feet fencing. Now to get the largest area, then he should use everything, use all, i.e. length times length. Now there's three pieces, x, x, and y, okay, i.e. 2x plus y. Should use everything, okay, should use all the fencing, i.e. so this should be the all the fencing 204,000 feet, so that we can indeed get a relation between x and y. So for instance, if we solve y in terms of x, then we get y is actually 2,500 minus 2x. Then we can substitute y to get E is actually area function of just one variable function of x. Replace y by 2,400 minus 2x. Okay. Now for two variable functions, so for one variable functions, then we can use the closed interval method. Okay, find its maximum. Okay, so first of all, we need to find how big x can be. Okay, how big x can be. So first of all, x should be greater than 0. Okay, next, y is also greater than 0. Okay, so actually we get 2x is less than 2,400. So this x should be bounded by above 1,200. Okay. Okay, so this is the 2,400x minus 2x squared. But then we differentiate. A prime x. This will be use differentiation rules. 2,400x, we get a 2,400. 2x squared, we get a 4x. Okay. You see, let a prime x be 0. Then we get 2,500 minus 4x is 0. It's very easy to solve for x. X is 600. The unit is feet. You see, now the interval is interval notation 0 to 600, 600 to 1,200. Then a derivative. So this you check is negative. Sorry, it's positive, it's negative. It's negative. So ex, this is increasing, then this is decreasing. So you see increasing, then decreasing. The graph looks like increasing and then decreasing. Okay, so we have maximum, local maximum, local max. Now back continuity, we don't actually need to check the other boundary, the two boundaries. The two boundary values should be trivial. Okay, of course you can check the two boundary values. In general, for practical problem, if we have one critical number, usually that gives us the optimization solution. Okay, because we only have one, the best possible solution. Usually just one solution. So here, Ex attains actually global maximum, or global maximum. Here the local max turns out to be global max. Attains its maximum, attains maximum at x equals 600 feet. Okay, then E 600, you find out area. Okay, in this case you can find y. Okay, y is 2,400 minus 2x, which is a 1,200. So this is x times y. This will be 600 feet times 1,200 feet. So you get 72 4 zeros feet squared. Okay, so this is 7.2 times 10 to the 5 feet squared. So this is actually the maximum area that the farmer can get ideally. Okay. You see, the general pattern to do this kind of optimization problem is, first step, read the problem carefully and make sure you understand it. And then the second step, try to plot a graph, okay? And then put the information inside. And then if something is changing, try to put variables inside. And then the next step, try to find the goal functions that you want to maximize or minimize, okay? And then if it's one variable function, then you just differentiate, find its maximum or minimum. If it is it has two or more variables, then what you try to do is use substitution, find the relationship between the variables, and then substitute the variables so that you get a one variable function. Then you do the algebra technique, find its maximum by the closed interval method. Then you find its maximum, okay, or minimum. Then you are done. So this is general pattern to do this kind of general procedure to do this kind of problem. Okay, let's see another problem. Okay, example. Okay, suppose we have a box. So suppose a box. Suppose we have a box with square base with a square base. And open top. Now we want this box have a fixed volume for some, for some purpose. Must have a volume of 32,000 centimeter cubed. Okay. Now we want to find the dimensions of the box such that we minimize its material. Find the dimensions of the box. That minimize the material used. That minimize the material, the amount of a material. Okay. Now, for this problem, we should make some reasonable assumption. For instance, the side and the base should be the same material. Okay, be the same material. Okay, be the same material. Then the amount of material used should be proportional to the area, to the surface area. Okay, adoption. So the base and the side should be the same material, and then the amount of material is just proportional to the surface area. Okay, to the surface area of the box. Okay, so amount of material should be proportional to surface area. The larger area, then the larger amount of material, surface area. So what we minimize, so we need to minimize the surface area. The surface area of the box. So we need to find the surface area. So we plot a box with, it's open top. Remember, it's open top. It's a square base. It's a square base with open top. Okay, so we plot a box with square base. Okay, so square base tells us the length and width should be the same. So we put the variables into the graph. So suppose it's let x be its length of the base. Okay, so its width is also x. Now, how about its height? Let's height be h. Okay, height be h. So its volume. So it's a volume. So what's the volume? The volume of V is base times base area times height. So it's a length times width times height. So it's x squared times h. Now remember, we should have the box should have a fixed volume. Okay, fixed volume. 32,000 centimeter cubed. Okay, so this is the volume. So we have a relation between x and h. Okay, so we have a relation between x and h. Then we want to minimize surface area. So what is surface area? Surface area. Surface area. E. What is surface area? Now here, remember, it's open top. Open top. Okay, open top. So there's no top. So the base. So the base is a square. So this is the base. Now the first size, what's the first size? Now this is h. The first size, you can find its area. So the first size are the same thing by symmetry. So the first size, the first rectangle is length times width, h times x. Okay. And then we have 4 rectangles. Okay, front, back, left, right. So we have 4. So we multiply 4. Okay, so this is the area. Okay, area. Now you see the area in the area function. Then we have 2 variables, x and h. X and h. Okay. Now 2 variable function is hard to manipulate. Then we try to use algebra, try to substitute one variable into another. Okay, so that we get a one variable function. Now what we should do is, do we substitute h or substitute x? Now here you see in the area function we only have one h, so it's easier if you actually substitute h. So we solve for h. Now from the volume relation we do have a relation between x and h. So we solve for h. We did it above. So h is 32,000 over x squared. Then we plug in. So we get ex. Area function as one variable function of x is 4 times h. H is 32,000 over x squared. Multiply x. And then simplify this. Okay, so this is x squared plus 4 times 32,000 over x, cancel a factor of x. So we have this number over x. Okay, then we need to find its minimum. Find its minimum. Okay. So what's the range of x? X, x will be positive. So negative thing doesn't make sense. Now x will be positive. This turns out to be the only restriction to x. X can be arbitrarily large. If the height is really small, although this is really nonsense. If x, so although we only have finite thing, but here it turns out x can be arbitrarily large in theory. Okay, then we differentiate, find its minimum. So we find its minimum. Find a derivative. A derivative x is find differentiate 2x plus 4 times. Use power rule. With power rule. X squared negative. Okay. Just negative 4 times the thing. Okay. Comes from chain rule and power rule. Okay. So you see, let a derivative. So this will be 2x minus 60 2000 x squared. Now we find critical numbers. Find critical numbers. Find critical numbers. Critical number. Critical number. Let a derivative be 0. Then we have 2x minus 64,000x over x squared should be 0. So we have x should be 64,000 over x squared. So we get a multiply both sides by x squared. Then we get x cubed. So be 64,000. Now the unit is meter centimeter cubed. Now you take cubic root. You get x is 4 times 4 cubic gives you 64. X will be 40. Now centimeter cube. Take cubic root. Then you get 40 centimeter. Okay. So you get x should be 40 centimeter. Okay. It turns out we only have one critical number. This should be gives us the solution. Okay. If you check. Okay. If you check by increasing decreasing test, it's very easy to check. Okay. From 0 to 40, from 40 to positive infinity. Then you see this derivative should be increase. So it's this you should get negative a derivative. This should be positive. Then ax is decreasing, then increasing. Then you see decreasing, increasing. Then you see you have local. Then you have minimum. Okay, minimum at x is 40 centimeter. Okay, 40 centimeter. So now the box has achieved its minimum surface area if x is 40. Okay, if x is 40 centimeter, then we find h. H is 32,000 over x squared. Okay, this actually you get 42,000 over 40 times 40. Okay, then you got 20. Okay, the unit is centimeter. Okay, centimeter. So the dimension of the box should be dimensions should be 40 centimeter times 40 centimeter times 20 centimeter. Okay. So that in this case, so that the amount of material is minimum, so that the amount of material, the surface area is minimum, the amount of material used is minimum, the amount of materials used is minimum, attains minimum. Okay, so this is this example. Okay, one more example. Let's look at this example. Okay, example. Let me quickly do this example because we have around 5 minutes. Okay, now suppose a box. Okay, suppose we have a fixed amount of material to make a box. If 1,200 centimeter materials is available. To make a box. with a square base and open top. Square base and open top. Now we want to maximize the volume. Find the largest possible volume. Volume of the box. Okay. Okay. Now this problem, we need to maximize the volume of the box. Here, the material used, is 1,200 centimeter squared material. Now, we need to find the volume V, the goal function. Again. So here we have this kind of a square base open top. Okay, suppose this is X, this is X. Height is H. So volume is H times X squared as we did, okay? So this is a goal that we want to maximize. Now how should we deal with surface area? First question is, to get the largest possible box, then we should use all the material, okay? We use all the material. So the material should not have some leftover, okay? So all the material, remember, when we get the surface area, there shouldn't be no leftover. Should not be any leftover of material. To get the largest possible. To get the largest possible. To get the largest box. The largest box. Okay, so in that case, all the material should be used to get the surface area. So surface area is X squared to the base plus 4, 4H times X. Okay, then we optimize H. Now here we solve for H. So you solve for H. Let me quickly do it. Move terms, and then solve for H divided by 4X. Divided by 4X. So we get this is actually H. Then you see V is H times X squared. Substitute to the volume function. So H is a denominator 4X, 1,200 minus X squared, multiply X squared. So let me quickly do that. So this will be X cancel X. So it's 1,200 minus X over 4 times X. So this will be 300 minus times X. So this will be 300X minus a quarter X cubed. Then you differentiate V prime as a function of X. Then you got a X. 300X, you get a 300. Then this got a 3X squared over 4. So let derivative be 0. Find the correct numbers. So 300 equal to 3 over 4 X squared. So X squared you get, so you get a 4X squared, 400 equals X squared. Okay, in that case, you get an X, solve for X is 20 centimeter. Okay, 20 centimeter. Then you check this actually, indeed, you get the maximum. You get the maximum. Okay, then V max equal to V20. Plug in 20. Now this actually you get plug in 20. 300 times 20 minus a quarter times 20 cubed. Okay, so this is 6,000 minus this is 8,000 divided by 2, divided by 4, so it's 2,000. So you get a 4,000. The unit is centimeter cubed. Okay, so when X is the dimension of the box is 20 centimeter times 20 centimeter. In that case, H, you solve for H. I guess H should be so H, plug in H. H is minus 400 over 40. So this should be So sorry, 80. So each should be 10 centimeter. So the dimension of the box is 20 times 20 times 2, 10 centimeters. Okay, so that the volume achieves its maximum volume 4,000 centimeter cubed. Okay. All right, let me stop here. Let me stop here for today.